Good afternoon, all of you. Yesterday, we have finished the introduction part of biochemistry. Today, we will discuss the experiment number first. The title is Introduction to Biochemistry and Clinical Pathology Laboratory. The prior concepts, curriculum contest, scope of work, planning, and assessment. New concept, Proposition 1 Laboratory equipment. Laboratory equipments are expected to develop intellectual skill, motor skill, and attitudes in students. Then the concept structure is here. Then a proposition second is a logical thinking. Logical thinking is developed in the student through system approach, content analysis, and sequential planning of laboratory work. This is a concept structure. Then there are two objectives, intellectual skill and motor skill. Intellectual skill, to understand the concept of working of each laboratory equipment. Second one is to identify corrosive irritant chemicals and to take care during its handling. Motor skills, ability to proper withdrawal and addition of proper reagents. Second one is ability to operate colorimeter, centrifuge, and microscope. During performing a biochemistry practical, we are going to handle the apparatus like a centrifuge, photoelectric colorimeter, spectrophotometer, and microscope. And to perform a different qualitative test, we will use charts. Then, in detail, we are going to see the structure, function of these apparatus: centrifuge, photoelectric colorimeter, spectrophotometer, and microscope. First, we will see a centrifuge. We have seen the centrifuge, how to use it, and its function. Okay, now we will see a spectrophotoelectric colorimeter.
What are photoelectric colorimeters? Describe the single beam photoelectric colorimeter. Photoelectric colorimeter is the instrument with the help of which quantitative analysis of colored solutions is possible. The photoelectric colorimeters are of two types: single beam photoelectric colorimeter and double beam photoelectric colorimeter. Single beam photoelectric colorimeter consists of following components. First, a tungsten lamp. A normal incandescent lamp with a tungsten filament is used. Second, a collimating convex lens. It collects the radiation from the source, and transmitted radiation will be traveling parallel to the principal axis because the source is kept exactly at the focus of the lens. Then there is a diaphragm. The function of diaphragm is to set 100% transmittance. Next comes filter. It is in the circular disc which is made up of number of colored glass patches. When the light from the source is allowed to pass through the filter, the unnecessary radiations are absorbed and we get light of only one color. Next is sample holder or cuvette. It is a rectangular, transparent container made up of glass or quartz. Then comes photocell. It is the component which converts the radiation into current. It converts the transmitted beam emerging from the sample into an electric current. This electrical pulse is due to the emission of electrons from the photocathode surface caused by the transmitted beam falling on the photoelectrode. And finally, signal indicator or readout meter or digital display. Generally, galvanometer is used for this purpose. It is a meter calibrated in 0 to 100% transmittance or absorbance unit. Some meters cover both absorbance and transmittance. The optical density or percentage transmittance can be read directly. So now let's discuss the working of this instrument. Light from the source, such as incandescent lamp with tungsten filament, passes through collimating convex lens and then through the adjustable diaphragm. By adjusting the diaphragm, the intensity of incident radiation can be altered to any required level. Light is then incident on the filter, which allows only a narrow band of the wavelength to pass through it. The solvent or the sample solution is placed in the cuvette, and transmitted light falls on the photocell, producing small current. The current is then incident on readout meter or dial, which reads transmittance or optical density. So how can we perform quantitative analysis by using this method? First, we take a blank solution, that is solvent in the cuvette, which has been properly cleaned, and insert it in the optical path of the instrument. As it is a blank solution, therefore there will be no absorption and light is fully transmitted. And then incident on photocell and galvanometer shows 100% transmittance. If there is any absorption due to impurities, this can be nullified by adjusting the reading of optical density to 0 or transmittance to 100%. Now remove the blank sample from the cuvette and put the sample solution, whose concentration is to be determined. When the light is incident on it, some radiations are absorbed and the remaining is transmitted, which is incident on photocell, which gives the optical density value or transmittance. If optical density or transmittance is known, by using Beer-Lambert's law, we can calculate the concentration of the solution. The Beer-Lambert's law is optical density is equals to absorbance is equals to log of I0 by IT is equals to minus log of T is equals to epsilon CL, where epsilon is molar absorptivity coefficient is a constant and L is the path length, which is also constant. Therefore, we can easily calculate concentration C. But single beam photoelectric colorimeter is having a lot of disadvantages. So what are these disadvantages? First, as the source of radiation is AC, that is alternating current, the fluctuation in the voltage causes fluctuation in readings. Second, as the solvent contains the impurities, which also absorbs the radiation, therefore, it is not possible to get the correct amount of light absorbed. Third, as filters are used which do not give 100% monochromatic light, Therefore, analysis is not accurate and has some errors. If you like this video, please click on the like button and also
हे आहे स्पेक्ट्रोफोटोमीटर. Spectrophotometer is an instrument that measures the amount of light absorbed by the sample. त्याचं principle काय आहे? Spectrophotometer techniques are mostly used to measure the concentration of solute in solution. By measuring the amount of light that is absorbed by the solution in cuvette placed in the spectrophotometer. म्हणजे स्पेक्ट्रोफोटोमीटरचं काम काय आहे की आपल्या सोल्युशनमध्ये सोल्यूटचं कॉन्सन्ट्रेशन किती आहे. म्हणजे फॉर एक्झाम्पल पाण्यात साखर विरघळली आहे, मग त्या पाण्यात एक्झॅक्ट साखरेचं प्रमाण किती हे मेजर करायचं काम कोण करता? स्पेक्ट्रोफोटोमीटर. हे स्पेक्ट्रोफोटोमीटरचं इन्स्ट्रुमेंटेशन आहे. म्हणजे ते एक्झॅक्ट कसं काम करतं आणि त्याचे पार्ट्स कोणते कोणते आहेत ते दाखवले. पहिला आहे लाईट सोर्स, नंतर लेन्स म्हणजे त्याला कॉल्युमेटर पण म्हणतात, मोनोक्रोमॅटर, वेवलेंथ सिलेक्टर म्हणजे स्लीट, आपलं सॅम्पल सोल्युशन ज्याच्यामध्ये आपण सोल्यूटचं कॉन्सन्ट्रेशन डिटेक्ट करणार आहे, नंतर डिटेक्टर, फोटोसेल पण म्हणायचं, आणि लास्ट वन इज डिजिटल डिस्प्ले किंवा मीटर. जेव्हा आपण लाईट सोर्स ऑन करतो तेव्हा त्याच्यातून वेगवेगळ्या वेवलेंथचे लाईट बाहेर पडणार, ते लेन्समधून पास होऊन मोनोक्रोमॅटरवरती येणार. मोनोक्रोमॅटरमध्ये लाईटचं स्प्लिटिंग होणार वेगवेगळ्या वेवलेंथच्या लाईटमध्ये. मग ते लाईट स्प्लिट झाल्यानंतर आपल्याला ज्या वेवलेंथची लाईट हवी आहे ते आपण वेवलेंथ सिलेक्टर किंवा स्लीट टाकून ते सिलेक्ट करू शकतो. मग ती लाईट आपल्या सॅम्पल सोल्युशनमध्ये पास होणार. मग सोल्यूट लाईट ॲब्सॉर्ब करेल आणि ते डिटेक्टरवर पडेल. मग डिटेक्टर मीटरवरती रीडआउट डिव्हाइस रीडिंग देईल. हे रीडिंग म्हणजेच सोल्यूटनी ॲब्सॉर्ब केलेलं ॲब्सॉर्बन्स. Now we will see the microscope, its parts and their uses.
Uses. A. The eyepiece, ocular, is the part of the microscope closest to your eyes, through which you look. It contains the ocular lens, which makes the image produced by the objective's lenses larger. An eyepiece may be labeled with its magnification or power, for example, 5x or 10x, meaning it enlarges 5 times or 10 times. D. The body tube holds the eyepiece in position over the revolving nosepiece and the objectives. The body tube may be straight up and down or slanted. C. The arm is the curved metal piece that holds the body tube in place over the stage and the base. D. The revolving nosepiece holds the objectives and allows you to change objectives while looking at a slide or sample. E. The objectives are the parts at the bottom of the body tube closest to the sample you are examining. Each objective has a lens and a tube-like holder, the mount. The longer mounts hold the stronger lenses, the high-power lenses. The shorter mounts hold the weaker lenses, the low-power lenses. Like the eyepieces, objectives also come in various parts. Microscope has several objectives, for example, 4x or 5x, 40x or 45x, and 100x. Some microscopes only have 1 or 2 objectives. F. The stage is the flat surface on which you put your slides or samples. G. The stage clips holds the slide in plate on the stage. H. Beneath the stage in all the besto microscope
have a condenser having standard diameter of 39.5 mm, which collects and concentrates the light before it passes through the sample. I. The iris diaphragm is used to control the diameter of the cone angle of the light transmitted onto the specimen. J. The coarse adjustment knob is the large knob used to adjust the position of the body tube, allowing you to quickly bring your sample slide into view. K. The fine adjustment knob is the small knob used to change the position of the body tube by making small adjustments to the focus of your sample. Almost all of our besto microscopes have both coarse and fine adjustment knobs, but some have only one knob. L. The mirror, located beneath the stage diaphragm, increases the amount of light shining through your sample or slide. Sometimes we use lamp plugged into an electrical outlet instead of mirror or reflector. M. The base of the microscope is the heavy bottom part. It supports all the other parts of the microscope. N. Substage adjustment knob is used to move condenser up and down.
So, we have seen the different apparatus we have to use during performing practicals: centrifuge, photoelectric colorimeter, spectrophotometer, and microscope. Here are the diagrams for these apparatus. In the observation, you have to write the different parts we have seen for these apparatus. Okay, and here we have completed our first experiment for BCP.